Good afternoon, everyone, and thank you for attending our Adding Keypads and Cables to Your Injection Molded Enclosure webinar. My name is Ryan Wood, the Content Marketing Manager here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel. We'll try to get to all of them at the end of the presentation. If we don't have time to go through all your questions, we'll be sure to reply back to you by email. Also, we'll be recording this webinar and posting both the recording and the slide deck on our website and our YouTube channel. Our presenter today is Stephen Goodman, our User Interface and Cable Assembly Product Manager. Stephen is a mechanical engineer with a Bachelor of Science and MBA from Northeastern. Here at Epic, Stephen works closely with customers to provide solutions to specific problems during design consultation and, where needed, helping with the creation of specific designs. So, without further ado, I'll pass it over to Stephen.
Thank you, Ryan. Hello, everyone. My name is Steve Goodman, and again, I'm one of the product managers here with Epic. So today we're going to be discussing ways to add keypads and cables to your injection molded enclosure. So for our agenda today, we'll be talking a bit about the materials and options to choose for the enclosure itself. Next, we'll be discussing ways and specific technologies of keypads and cables to add to your enclosures. Next, we'll touch on ingress protection and ways to electrically shield these enclosures. We'll touch on some examples and design solutions. And lastly, review ways to get started with your custom build. First, we'll be touching on materials and options for the injection molded enclosures themselves. So most of the injection molding processes we support here at Epic are using thermoplastics. The use of injection molding is a wildly common technique, largely because it's inexpensive, it's readily available, and most importantly, it has an excellent weight to strength ratio. The performance of these materials has been tested over many years, showing they're wildly appropriate for these types of high volume, low cost applications. The products that use injection molded enclosures include any kind of box builds, devices that house and enclose a PCBA. These could be any number of test apparatus, both for consumer products or even for industrial control equipment. A lot of these items will have a top and a bottom, or maybe a front and back, a housing and a lid. It's typically a clamshell or two-piece design that somehow goes together. And most of the actual materials we're using in the injection molded process are an ABS, a polycarbonate, or even a blend of the two. In addition, there's some other thermoplastics we can support, not to mention polypropylene, polyethylene, and so forth. It's important to note that there are dozens of brand name materials out there from globally known companies like Covestro, Sabic, but in addition, there are locally sourced, lower cost equivalent materials that sometimes make sense depending on what the program objectives, timeline, and budget are. More about the benefits of using thermoplastics and injection molding. Again, these materials have an extremely high strength to weight ratio. They're also wildly inexpensive, with some of the raw materials costing pennies or dollars. Another benefit to these types of materials is the fact that many use a UL recognized material that comes with existing flammability ratings, and additional health and safety qualifications, allowing these products to be used in a wide range of industries. Another benefit to using these thermoplastics in injection molding is the fact that there is tabulated data available for the material properties of these compounds. So for example, many of today's solid modeling packages that engineers and designers use, by putting in a solid model into the computer, we can assign material properties to those designs and then subject them to an FEA, finite element analysis type stress analysis. And in doing so, we can put simulation loads on these devices, on the enclosures, to go and better predict failure modes, stress concentrations, and how these are going to behave and deflect in the use of whatever these projects and products are being used for. The one challenge with using injection molded plastics like this is the fact that you need an actual three-dimensional step file or digital file to go and make these. 2D drawings can be used, but an engineer is typically needed to go convert that into a step model and then go build from that. Additionally, hard tooling is required for these types of injection molded processes. So unfortunately, that does not mean that they are a great fit for rapid prototyping and that sort of thing. If that is required, 3D printing is an excellent choice to go and make injection molded-esque type products, but doing that quickly and for very inexpensively in the grand scheme of things. It's important to note that using 3D printed enclosures, it's not the holy grail, it's not the silver bullet, but they can be used early and often because they're so inexpensive, because we can go online and upload a step model into the number of prototype facilities out there on the internet and have these parts built in a couple days to a couple weeks for relatively short money. Because this is an additive manufacturing process, there's no tooling needed. Layer by layer, these 3D printed enclosures are built up and the materials are fused together with some typical post-processing that's needed to go and give the appearance of a smooth injection molded surface. So 3D printing has come a long ways in the last 10 to 20 years, but today it seems every engineer that I work with either has one in their lab at the office or even has one of these at home. Some of the materials that are used include polycarbonate, ABS, nylon, and also PLA type filaments. The most important note when considering a 3D printed enclosure before you switch to an injection molded enclosure is the fact that the cosmetics and surface finish of the 3D printed enclosure will not be the same. They're going to be rougher, they're going to look different. So depending on what you're doing with these products, 3D printing may or may not be the appropriate solution. It's not just plastics that you can 3D print. Technically, we can 3D print rubber. My opinion, though, is it's not the same. It works, but it doesn't give you the wildly elastic behavior that silicone has. So they're good for fit checks, they're good for preliminary tests, and so forth. If 3D printing doesn't give you the material properties you need in an elastomer, for under $100 in a few days, you can go and design a mold from a 3D printer, build it, and then buy a hobbyist kit of 2-part silicone, mix the material, pour it, and just in a couple days, get your own silicone elastomer molded part that looks pretty good, all things considered. But obviously, surface finish, porosity, any number of those things are not going to be the same as when you compression mold a silicone elastomer member. So it's important to note that you can 3D print a mold and use some of these prototype and silicone compounds for the initial stages, but they do not do the same, or they do not have the same benefits, behavior, and so forth as the production-worthy silicone elastomers. But definitely a good consideration if you want to do a fit check with a grommet, with a new gasket, or a keypad. More on keypads to add to your enclosures. So all of the technologies that are used, the two most common switch types for custom switch technologies added to enclosures are 1, membrane switches, and 2, silicone elastomer keypads. A membrane switch is an extremely common, low-cost, high-reliability device that is used in all industries. They're typically pretty low tech in the grand scheme of things. They just act as a series of normally open switches, sometimes designed in a switch matrix array. And even on top of that, we'll add LEDs and other surface mount devices to the circuit if needed. Taking these membrane switches and removing the actual circuit material, one's left with either a graphic overlay or a silicone rubber keypad. The latter are typically compression molded silicone elastomer. Most of these keypads are about 50, 55 Shore A on the hardness scale. Going higher on the Shore A hardness scale, the keypad becomes more rigid. It takes more force to push the key to get the same amount of translation of the key. Whereas going lower in the Shore A scale, the material is softer, but then will become susceptible to failure or stretching or damage over time. So it's important here when sizing and developing a custom keypad to try to go and build it and test it and come up with some assessment or ways to develop a quantitative analysis to give the team feedback if the design, if the hardness and so forth is appropriate. If dialing in the rubber is not enough, the actual dome switch force value itself can be changed, whether it's 150 grams of force or 200 grams or even higher. The actual force rating of the dome can change the overall perceived tactile feel of the keypad. So it's not just rubber that we can dial in to get the right tactile sensation. Lastly, a lot of these membrane switches and keypads use some kind of backlighting, whether that's an on-off button to show whether a system is energized, could be backlighting for keys to make sure that the user can read the keys and that it's available and accessible in low light conditions. Most of these backlighting techniques are achieved with LEDs. Sometimes they're discrete LEDs behind a window. Other times they're a side-firing LED that goes and shoots horizontally through the layers of the membrane switch, and in doing so, helps backlight several key icons and features. Keypads attach to enclosures several different ways. The two most common are one, using adhesive, and two, using a mechanical attachment method like a fastener or a through hole with a screw. By and large, adhesives are the most common ways to add these types of keypads to enclosures. It allows them to be flush mount. The adhesives are inexpensive, they're reliable, and depending on the application, some adhesives are wildly strong, some of which we recommend for military and aerospace applications that are almost permanent attachments. We'll need to do some special processes just to get the keypad off of there. So when trying to develop a way to attach a keypad to an enclosure, it's important to identify if a mounting hole is needed and if those mounting holes are needed actually in the keypad itself. Once the keypad has been placed onto the enclosure, there needs to be a way to get the electrical signal of the keypad. Usually it's switches being on and off, or maybe an LED being on and off. Some way we need to get that electrical signal into the enclosure. One of the most common ways we accomplish this is using a zip tail. Zip tails are zero insertion force, low complexity connections, and the benefit there is that they're common on the flexible flat cables that attach to all membrane switches, and they're easy to route into a very small slit in the enclosure, and in doing so, helping us develop a watertight and waterproof seal. It's important to note that these are going to be flush mounted, and although the overall thickness of a membrane or keypad is not that thick, right? These can be 30 thousandths of an inch thick to 100 thousandths of an inch thick, maybe half an inch depending on the keypad height. But it's important to go and design a recessed pocket into the enclosure so that once installed, you have a nice, smooth, flat surface, and the membrane fits completely flush on the enclosure. Additionally, we strongly recommend to keep the shape of your membrane or keypad simple. And what we mean by that is it should be a shape or a contour or a feature that's easy to define. So if it's a shape that we can define on a 2D drawing with length, width, radii, that helps the design, the inspection, and the production. Whereas if you have a unique contour with a shape that's difficult to define, that can create trouble getting those made and doing fit checks. Keeping it simple here is definitely a way to go and reduce risk and drive cost out, especially early in the project. More about backlighting options here. Since LEDs are among the most common types, and considering they're available in a number of package size, we recommend to our customers that you choose an 0603 or larger package size for LEDs. Now, there are some that are smaller, but the goal here is not to design a keypad that's impossible to assemble. Secondly, a lot of these prototypes are hand-built and hand-populated by one of our operators here out on the floor in New Bedford. Using an 0603 as the smallest LED size is a good way to make sure that we can build those quickly and that we don't need a specialty assembly jig to go and repeatedly make these. Once the LED is designed, affixed to the circuit, there are times where we need to bring that light to the surface of the enclosure. Light pipes and other features like that, shown in the upper right-hand portion of the screen, are excellent ways to take a surface-mounted LED and bring that light to the surface of the enclosure for the user to go and obtain whatever information that LED is telling them. If an individual LED doesn't accomplish what we're trying to do backlight-wise, light guide film is another low-cost technique. We can go and achieve a uniform backlight across a larger area of a keypad. Next, we'll touch on some cabling considerations for enclosures. So what's important here in terms of cables is the fact it's important not to reinvent the wheel. And what that means is there are dozens, if not hundreds, of off-the-shelf standard power and data cables that are out there. Whether it's the connector, the cable, the panel-mounted plug, any number of those, using an off-the-shelf option drastically reduces cost and risk. Obviously, there's times where you don't want an off-the-shelf option and you need some level of customization. So taking one of these off-the-shelf existing connectors or interfaces and modifying it is a low-risk way to go and get the customization one may need for a certain project while also leveraging what's already been used and works in the field. Additionally, some of these connectors and products may already have an existing IP rating, flammability rating, and are already UL listed. So what this means is if you need a power cable, rather than developing your own and having to go through certain product safety tests, we can go choose an existing off-the-shelf or existing designed plug, receptacle, and cable interface. And when all else fails, we suggest making something that works. And what we mean by that is walk around your office, walk around the lab, find something you think will work, cut it up, try it, see how it goes. For a few $100s in a few days' time, one can go to the online distributors of the world and buy a whole bunch of hardware and try to make something work. That's important when you're up against a tight timeline, a budget, or a tooling investment that may not be something you want to invest in after all. So once we identify a connector scheme that we're going to use, the next thing to consider is what type of wire, or actually conductor, is best for the application. So there's dozens and dozens of types of wires that we can use in these applications, but generally speaking, most are either a single conductor or a multi-conductor cable, many of which we make ourselves with UL and flammability ratings. We can also add several different types of shielding configurations to the cables depending on what the enclosure or box is doing. So this could be a braided shield, this could be a mylar foil shield, and the addition of a drain wire. All of which in concert will give a certain performance characteristic to the system. If a standard wire is not available, there are custom extrusions that may be an appropriate option. These aren't always the lowest cost, nor are they always the fastest, but a custom extrusion may be the only option if you need 10 different twisted pairs within a braided shield with a drain wire with a certain outer diameter for a raw jacket material. Additionally, we can mix and match any combination of wire size, color, and material based on what our customers need. And some of these may already have an existing UL compliance that we can leverage, and if not, we can make non-UL custom extrusions in as little as 3 weeks. For all of these options, Epic would supply a data sheet to our customers and even a material sample for some initial testing. Once the cable has been spec'd in, it's important to note that there are overmold designs that we can add to the cable assembly with $0 NRE tooling. And what that means is since we have hundreds of house tools readily available at our overmold facility, if we're using a common connector like an RJ45, like an M12, like a USB-A, the odds are we already have an overmold tool that's designed, built, and ready for use, eliminating thousands of dollars and weeks worth of lead time. If we are adding a custom overmold with a custom tool, further customization can be added. We can add artwork, logos. All our customers need to send us is a rough spec and an AI file, an Adobe Illustrator file, and we can go and take that artwork and logo and actually build that into our tool so that once we yield an overmolded part, that logo or artwork will come out raised, recessed, or to whatever our customers' requests are. Next, we're going to touch on some ingress protection means and ways to shield our boxes. When it comes to EMI shielding, this is largely an area of black magic for a lot of the engineers that we work with. We don't know necessarily if a unit will pass radiated emissions or susceptibility, but it seems to be the boogeyman for most. So what we end up doing is ending up adding layers of shielding to the enclosure, to the PCBA, to the cables themselves, all in an effort to make sure that once we finally have a product built and brought to a qualification lab, that we have the highest probability of passing those tests as possible. So radiated emissions and susceptibility, what we're safeguarding against is electromagnetic interference coming into the box or leaving the box and somehow impacting system performance, both of our widget that we're designing, but also the other products around them. So there's several specifications that touch on these types of performance requirements, and they range from product safety level requirements to military and aerospace specs, such as MIL Standard 810, DO 160, and MIL Standard 461. All in all, each one of these test requirements is application specific. So if you're building a test box that's going to go and be used on the ground for the Air Force, they're going to have different EMI considerations and worries versus something that's going to be used in a medical facility or in the operating room. Another concern when developing these types of devices is ingress protection. And this isn't just water, it's also dust, sand, salt, and any type of contaminant that can get into the device, get into the switches, and hinder performance. When we go and develop an elastomeric keypad, there's features that we can add to the surface of these keypads that act as a sealing surface. And when designed right and assembled correctly to a flat surface, we can achieve IP67 or higher ratings when designed right. Once we build and test, it may be clear that additional gasketing may be necessary to completely solve all program objectives. But by and large, most of this is accomplished with some sort of combination of mechanical fasteners like bolts and screws, or adhesives like the PSA, the 3M467, or an RTV compound. But most importantly, as these photos will show, if a leak test is performed at the system level, you may get different results, whereas if you test a subassembly. And this is important because the goal of performing an ingress protection test is to represent actual real-world conditions. Now, once the test is complete, it's important to have clear pass-fail criteria. It's important to understand if the system performance is impacted by the ingress of whatever the medium is. Does this ingress constitute a test failure? We all know designing an IP67 enclosure is a very strict and difficult test to pass. So if there's a few drips or leaks of water that get into your enclosure, does that constitute a failure? Working with the design agency, working with the end customer, these are all discussion points and considerations that need to be addressed early in the project. Otherwise, you could have the risk of a false test failure, and in doing so, chew up a lot of time and resources. Next, we'll touch on some examples and design solutions of ways to add keypads and cables to your injection molded enclosure. So the first and one of the most simple ways to add a cable to an enclosure is the use of a very low cost and widely used item called a cord grip. A cord grip, also known as a cable gland, is this small device in the upper right-hand portion of the screen here. And what they are is basically a nut and bolt mated part that envelops the cable jacket and helps secure it, creating some kind of strain relief and seal. And each one of these cord grips are sized to a cable outer diameter as well as a through hole in your panel. And there are dozens and dozens and hundreds of options of these that exist. The drawback here is that at volume, these cord grips can actually be expensive. And what we mean by that is if you go and spend $2,000 in the investment of hard tooling for an overmold, the recurring cost for adding an overmold may only be 20 cents. So if you're building 10,000 harnesses, there's a huge return on investment paying for the overmold and strain relief instead of choosing an off-the-shelf cord grip. Now, if you're building 5 or 10, a custom overmold may not make sense. Ultimately, we can help recommend any sort of strain relief or way to attach to an enclosure as long as we understand what your customer is trying to accomplish. But we have dozens of existing standard and readily available designs to choose from. Now, some of these overmolds can be quite small and delicate, This example here is just a few millimeters across and is exceptionally tight tolerance in the grand scheme of things. But for these types of products, we can support them. Let us help you study the interface and include tolerances that are achievable. The last thing we want to do is throw a too tight tolerance here on an overmold such that it doesn't fit properly with the machined or molded enclosure that this area of the overmold slides into. Other custom strain relief options include this mouse hole type slot in the enclosure where it's just a U-shaped slot and then the lid comes down to seal. But there's different ways and techniques we can go and develop the cross-section for that overmold in that particular region. So as long as we know where on the overall length of the overmold and cable we want to add these features, and there's a way to geometrically define this shape, then we can be successful making this for you. A lot of the concern with adding a custom overmold or strain relief to a cable is making sure that the overmold doesn't just slide down the cable jacket. That will not serve the design intent. So there's different things that we can do, both matching the overmold material to the cable jacket, and in doing so achieving a chemical bond, or adding things like crimp rings or other star type washers within the overmold, and then adding the cosmetic overmold on the outside, and in doing so helping achieve some kind of better pull force rating or reducing the slip of that overmold onto the cable jacket. Other options to add keypads and cable assemblies to enclosures include the use of a rigid circuit board. Most of these PCBs are 2 layers, sometimes 4, but they're typically not the 12-layer highly complex board that we could do, since most of these are supporting low voltage and some type of key button strike and backlighting data that's being passed to and from the systems here. A lot of these will use a dome switch and a hard keycap, but others will actually use an off-the-shelf tactile switch. The way that those work is it's a standalone surface-mounted device that comes as a single package, most of which use some kind of spring or magnet assembly inside to achieve the tactile sensation. And they're typically normally open and wait for the user to press the button. But these are nice options when paired with a rigid board and some kind of hard keycap that itself is either injection molded or made with a high durometer silicone elastomer. And lastly, one of the benefits of using these types of rigid keycaps is the fact that with one mold, you can achieve the shape of the key. You can then go pad print or silk screen the different markings. So for example, you can have a 12-button keypad with 1 through 9, 0, and then a star and hashtag. But you could have all of these made from one tool and then designed a set of pad printing stamps to go and mark each key with whatever numbers, letters, or icons that are needed. But the benefit there is you're using one hard tooled injection molded keycap, and then you're just paying a small fee for the tooling change to go swap out the different pad print stamps that are used. Here's another design with an injection molded box with a small board and a surface mounted off-the-shelf switch here. So in this particular example, actually, this switch was mounted to the lid of the enclosure using a small nut that's mounted from the rear. And on this one, we had some challenges figuring out how to connect it to the board. So our team developed a simple way just to have a small 2-position single row connector added, and we're going to put a couple small leads jumpered from the pins there to the switch. But the benefit here of this type of design is that this was originally designed and built and assembled using all 3D printed and quick turn prototype means. Once assembled and the circuit was proved out, it's then clear it's time to invest in injection molded or hard tooled device and then a production worthy rigid board. Some of the key feedback on products like this is modeling these in the computer. You can learn a lot, you can get a lot of data. However, it's not until you actually assemble one, until you figure out that maybe you need a little more clearance for a fastener to be installed, or maybe access to the bolt head is a little difficult. Either way, building one of these, testing it out, is a great way to go and get early feedback on how this is all going to go together and be assembled. Here's a project where we're developing an indoor use only heavy duty power cable. Some of our customers' concerns here were mostly drop testing concerns, as well as the radiated emissions and susceptibility concerns. This apparatus was designed to operate in excess of 200 volts AC at 30 amps, meaning a high power application, and we needed to go through the entire design here and make sure everything was sized for the amount of power that this was planning to handle. The benefit here is that Epic can go and use an off-the-shelf receptacle. We can use a custom injection molded enclosure. We're making the PCBA, and then we're actually using our own UL wire with 2 custom overmolds on the pigtail side of this. So we can go plug this into a 220 volt AC outlet and have it be wired and strain relieved to the enclosure here. When it comes to the lid, there's a couple ways to attach the lid, most of which either include or involve some type of mechanical fasteners or something as clever as ultrasonic welding the lid on. The problem with the latter is it's more of a permanent assembly technique, which is not a bad thing when you have such high power in a small device to be used in the home. But still, ultrasonic welding would need some careful considerations on how we go and rework these once they're assembled if we need to get into them and either reprogram them or troubleshoot the board. At this point, we also need to consider what is going on the inside of the device here. Is there cooling? Is there a fan? Is there some kind of need to add venting or other slots to cool the device? So adding these is no problem early in the process. And even once we're tooled up, modifying the injection molded tools to go and support a few slits or vent holes is really not a problem. Next, we're going to talk a bit about how to get started with your custom build. So in order to take the first steps, our customers need to do their due diligence. We need to know what industry you're trying to support, and in doing so, what agency approvals are necessary. It's also important to note where this is going to be used or sold. If we're only targeting a device to be sold in North America, there's certain requirements and listings we need to go and comply to. Whereas if this is going to be sold in Europe, Asia, other parts of the world, there may or may not be additional product safety and certifications that are necessary to go and bring a product like this to market. So this is important because if you get 6 months into a build targeting a device to be used only in North America, there may be significant design changes that are required for that device to be sold elsewhere. Spend the time early to figure out what industry and agency approvals are necessary. And in doing so, that helps us and you, the customer, establish those high-level, system-level requirements. Another thing that we strongly recommend before moving forward is spend time to build the prototypes. And we don't mean just 3D print something for look and feel. Go and make something that works. It doesn't need to be perfect. There's going to be a lot of iterations and design changes over time, but spend the time, invest. A quick mock assembly in the computer, you can learn a lot. You can see interface issues between two members that once assembled in the computer may lead to assembly challenges. However, you're not going to learn everything until you actually go and build a part. So we strongly encourage our customers to go and spend the time and research this. Build prototypes before you move to a low rate initial production. It really helps to flush out design issues early in the process. Lastly, we strongly suggest partnering with one or as few vendors as possible to reduce some of the integration challenges that come with the new product release. And what we mean by that is if you're sourcing your board from one vendor, your touchscreen from another, your enclosure from a third, and then trying to marry all that together with a custom gasket or a rubber keypad, if there are dimensional issues or tolerance issues, those aren't going to come to the surface until you go to assemble this whole thing. Whereas vendors like Epic, as a full service manufacturing partner, we can help flush out some of those integration challenges early so that when we're building it, when we're going and making those initial prototypes, we can help relay areas of risk and concerns so that we don't end up 6-8 months into a project with a fit check issue. Another thing we strongly recommend before moving forward is using 3D printed to our advantage. Now, what this means is it's fast, it's inexpensive, and these 3D printers are everywhere. We probably have 8 of them or so out back in our lab here. But it's not the holy grail. It's not going to do everything. But like we've said throughout the webinar today, using 3D printing will help you get to market faster with less risk when we're smart about using those. So that's important because you need to understand the process limitations with some of the 3D printers. If you're planning to do an IP67 leak test on an enclosure that has been 3D printed, a lot of those enclosures have porosity and small holes with the layer lines that they're going to leak on their own. Or some of the materials themselves may not be stable with whatever the medium is you're testing, whether it's alcohol or water. Do your due diligence and tread carefully when using 3D printed members, but know that they will severely help get to market faster for less money with less risk when used appropriately. So when kicking off a project, we ask our customers to complete one of several inquiry forms based on the particular product. This information is typically captured by our sales team, documented, and then brought to the product manager group to go and help develop these opportunities and move them forward with our customers. So some of the specific information that we need to launch an enclosure project like this would be some sort of statement of work or a SOW. And that doesn't need to be extensive, but depending on the breadth of that document, it may require a subsequent discussion with our technical team, with our sales team, to really get our arms around the scope of work and what's involved. Another thing this helps us do is perform a manufacturability assessment. And what that means is we don't want to get 4 months into a project with you, come to find out that this is not something that can be built. We want to identify things that can't be built early on. And maybe it's a size issue, maybe it's a performance issue, maybe it's how this is going to be used or where it will be used. But these are all things that we want to work with you, our customer, on to better understand, because ultimately our goal here is to develop a set of engineering data that is either compliant or approaches what you're trying to do in the statement of work. And then we will use that engineering data to communicate back to you, our customer, to confirm the scope of work and regurgitate it back to you. And additionally, we'll use that data to build, to inspect, and then to go ahead and over time, iteratively make the product better by driving out design risk and any number of design challenges that can come up over the course of a build. Give us the requirements and let us figure out how to build it, and we'll work with you to bring this product to market. So, our summary for today has been: 1, plan for several rounds of prototypes. Use 3D printing. Do fit checks and testing. Spend the time up front to build some units to get some data. You will not be successful making a product like this if you plan one device, one round of edits. It's inevitable something happens, a change of scope, something with your customer, something in the market or the environment. Things change over time. So it's important to be able to quickly and develop new units, test them, check them, and go ahead and get real-world data before moving forward. Additionally, we want to leverage existing and readily available materials and processes. We don't want to reinvent the wheel. It adds risk, complexity, and the net benefit isn't necessarily there. So we only want to add customization to these products where it makes sense. Spend time understanding the IP requirements, the ingress protection rating, and what you're trying to accomplish overall in the waterproofness of whatever the device is. Spend time to figure out what the pass-fail criteria are. There is nothing more painful than a project to be told that your box leaks, but then only to come find out it's not a big deal. The design is robust enough to handle a little bit of water ingress. So in doing so, you've then spent the last 3 months trying to optimize a seal when all the while it doesn't really affect the system performance. So understand what the clear pass-fail criteria are. And lastly, our ultimate goal as a production partner would be to build production-worthy samples as fast as possible. And what that means is 3D printed parts are nice. We want to use those as needed, but we want to use those devices and prototypes as a way, as a path, as a GPS to get production-worthy samples with hard tooling built as fast as possible, because those are where we see the production tolerances and performance. Next, I'm handing it over to Ryan to talk a bit about our products.
Thank you, Stephen. While we review the questions that came in, I want to briefly mention some of the additional product solutions that we offer here at Epic, such as custom battery packs, flex and rigid flex PCBs, printed circuit boards, CNC machine parts, user interfaces, flexible heaters, and our energy-efficient fans and motors. Now I will pass it back over to Stephen to go over some of the questions that came in.
Thank you, Ryan. All right. So first question here is, what's your electrical test plan look like for these types of productions? For our electrical test plan, there's 2 ways to approach this. One is there's basic wiring, continuity, IPC 620 type tests that we can perform, most of which we're just using a multimeter, and we're probing, we're checking continuity, we're making sure that electrically it's wired right. That's standard, that's a given, and we do that on every product. But some of our customers will require high pot or some other high complexity tests that can be done with some of our test apparatus. Some customers have displays or embedded systems, software that needs to be flashed. So sometimes it's more complex than just turning a switch on and off. So to answer the question, some of our projects will require a complete functional test, largely defined by our customer, and other ones it's just a pretty simple probing type test where we're using a conventional multimeter. But it largely depends on what's involved in the box build and what our customers need for requirements. Next question is, do you recommend drop testing, and when do you need to perform this test? So yes, absolutely, we recommend drop testing. There's formal shipping and handling tests that can be done. Some of these tests are derived from ISTA standards, but the goal here is to simulate real world abuse. And this is more than just kicking a box off the loading dock. It's plugging it in, unplugging it, using the product, dropping it from a table 10 times and see what happens, dropping it on all corners and documenting the results. Our suggestion here is don't overcomplicate drop testing and the needs there, but it is important to get some type of real world data on this. Next question we have is, can you color match the plastic to a powder coated aluminum, and what's that process look like? Yes, absolutely. We can color match any of the thermoplastics or silicone elastomers that we mold. Typically, Epic defines these colors as a Pantone color, an RGB color. We need some way to define the color. The challenge is if you colorize or print the same Pantone color on a powder-coated aluminum and do that on a ABS polycarbonate blend, and then do that with like a silicone elastomer keypad, you could have three different colors, even though all three are using the same Pantone. And what's important there is that the actual medium you're colorizing has very slight tendencies to look a certain way or the other. So if color matching is a concern, and you have different materials like a powder-coated aluminum next to a silicone elastomer keypad, two ways we can approach it. One would be to get an actual Pantone color that your team, your marketing team, and stakeholders are good with. Or two, give us literally a swatch or a coupon, and we will take that and color match the material direct to that. So giving us a coupon may be the best way to go and give it the exact color match specs we need. Problem is, we're going to need to hang on to that coupon indefinitely, and each batch do a color match to each one to make sure our colorization is dialed in. Next question here. We are using a NEMA 515 like the one you showed in the slides. Can you make those with custom strain relief, and how long does that take? So a NEMA 515 is a pretty standard like wall outlet you plug into your house to charge whatever you have, your phone, your stereo, television. That's the most common electrical plug here in North America. We have hard tooling for those. It's typically free to use. So if a custom strain relief is needed, then something like that we can help design and build in just a few weeks. I think more than anything, we want to understand what the specific customization is, and if it's something that we need to go and make a whole new tool for, or if it's something where we can just modify an existing tool and work with that. But again, these are typically pretty quick processes where the actual time for us to make the tool and dial in the tool performance is nothing more than 3 or 4 weeks. Next question here is, what's your choice for bolts and screws for a removable lid, and what if we want to ultrasonic weld the lid? So for bolts and screws, I think it really what determines this is if the designer wants the lid to be removable and by who. If this is something that is not intended to be field serviceable, a more permanent attachment method like an ultrasonic weld is appropriate. We can use an adhesive or an RTV on the seal there to limit, the removal of the lid or maybe tamper-proof it. Or this could be something where you're encouraging people to be able to take it off, and if so, then we'd recommend maybe a cap head or a pan head type bolt with a mating helicoil insert that's pressed into the enclosure. Dodge inserts are a common name for those, but what we would do is we try to dial in the type of fastener and then how the threads are going to engage the other side of the enclosure. If cost is an extreme concern, we don't always need to add the helicoils. They're not typically a cost driver, but we could use a thread-formed fastener and then design the mating plastic part just to make sure that the fastener interferes with the material there, and that the thread-formed features on the fastener can go and engage the material and cut the material and basically self-tap itself and make a hole there. And that is all we have time for today. I wanted to thank you, everyone, for attending the webinar. And I'm sorry if we weren't able to get to your question, but please reach out to our team, send in your questions, and we'll get back to you as soon as possible with some type of feedback. Thank you, everyone, and have a great day.